All right. So yeah. So question was for paper reviews. There will be a Google form. So for 4 questions, you need to answer them. You need to select the paper and then answer those 4 questions, and that's it. We would do it per presentation groups. Since group 1 and 2, like the topic 1 and 2 are together, so you just pick 3 out of those 2 topics, and then submit. And then you do the same for topic 3 and topic 4 and topic 5. So 12 papers in total.
The topic 1 and topic 2 are on the same day, so
Yeah,
combined they only need.
combine 3.
Okay.
Yeah. Good. Any other questions? All right. Okay, so we want to talk about transient execution attacks today. Sorry, this is forgot to update them. But so we're gonna shift our focus into security concepts on transient execution attacks. Let me full screen this. Perfect. Okay, so reminder that we're trying to cover a lot of things here. We talked about front end and the back end, and a little bit of memory. Also, if you remember, we gave you some background on cache attacks, side channel attacks, attacks and defenses. And you're going to learn a little bit more about cache side channel attacks and defenses next week as well in the paper presentations. So the goal today is talking about how this out of order backend can be misused by an adversary. And this is the story of transient execution attacks, or sometimes called microarchitectural attacks, which was around for some time. Generally, side channel attacks was around for quite some time, but until 2018, 2019, it was like it's exploded by introduction of 2 seminal attacks called Spectre and Meltdown, which kind of came out almost around the same time, which in some extent was independently discovered. And after Spectre and Meltdown came out, and many different variation of these speculative or transient execution attacks. Attacks like Foreshadow, and then multiple version of Foreshadow. Spectre itself had a bunch of different variants, variant 1 and variant 2 and variant 5, and so on and so forth. And then came out tons of other attacks afterwards, like Zombie Load and Riddle and LBI and so on and so forth, and it's still going. So it's to this day, there is still every major security conference you will see an attack. We will talk about kind of like the main structure of all of these attacks, because generally they're kind of like based on some fundamental assumptions. And then we're going to talk about next time we're going to talk about how to defend against them. We're going to talk a little bit about defense as well, but we're going to mainly talk about that. Before doing that, we're also going to talk a little bit about just the general memory isolation and security, because essentially what these transient execution attacks do is they're breaking that isolation assumption. So we're going to give you a little bit of background and detour on that as well. So all of that is really based on this fundamental assumption that I'm showing you in this slide, is that we generally like to have an in-order front end and an out-of-order back end for performance reasons. And then the big problem that is coming out for out-of-order execution is there is various reasons that we need to roll things back, right? So we either predict, or there is an exception, there is an interrupt, there's a context switch, and so on and so forth. Since we kind of like, let things go in any order that they want, there are many scenarios that we need to roll things back, right? And then we discussed last time that how we actually do this, and there are many optimization for it, and so on and so forth. But unfortunately, what happens as a result of this rolling back is that it creates what's been generally called as transient windows. Okay, what is a transient windows? Transient windows is this period that you make a speculation. So you have a bunch of different instruction, and you have one instruction here. Let's say it's a branch, And based on this branch, you make some guess, right? So for example, you say that, okay, this branch is not going to be taken, so I'm going to run some instructions, okay? And if this is your time, then what will happen is that from the time that you make this speculation to the time that this branch is resolved, resolve means either you know that you make a correct decision or you realize that, oh, you made a mistake. There is a window of few cycles, right? How long this window is, it depends on that particular operand for the branch. If the operand, for example, is coming from main memory, it takes as long as the entire memory access. If it's a register, then it's going to be instant. And then it could be like the branch itself might be also dependent on some prior instructions. So those might also take some time. So this window of how long this window is really depends on the microarchitecture and the operands of your branch. The important thing here is that the processor never stops executing things during this window, right? So that's the whole point and the whole advantage of out of order execution, that you don't want to wait for the branches. So you make some decision, either take it or not take it, doesn't even matter. And you start executing these instructions. These instructions, as we have said before, these are speculative instructions, okay? So this speculative instructions, you just go through the pipeline, and the fundamental limitations of modern processors is that these speculative instructions are, since they are not really going to be committed, it's not clear whether they're going to be committed. Many of the regular checks that we apply to instructions are not applied to them, because generally the rule of thumb is you apply things such as access policy and all that when you commit an instruction. There's no need to do things beforehand, because that actually goes through the critical path of the instruction. So you only do checks when the instruction is actually going to be committed, and it's safe in terms of like safety and correctness. That's great, because again, you know that if the instruction is not going to be committed, you don't care that if you know what sort of checks you need to run. But if the instruction is going to be committed, then you're going to run those checks, and if something happens, you're going to create an exception. So that was kind of like the main rule and golden kind of the main reason, the main design methodology of modern processors for many years. Okay, but then what happens with this transient execution attacks is that the attacker said that, oh, okay, so you're telling me that you're not going to check which instructions I'm going to run here. Then I'm going to run backy instructions here. Basically, I'm going to try to access kernel. I'm going to try to access another process, memory units and all that. I'm going to run all of those things in this window. And since you're not checking, then nothing's going to happen. Of course, once they're going to be committed, you're going to realize. But the cool thing about these attacks is that they have this methods to kind of transfer this into some channel and then use that channel to send it out. So for example, the common way of doing this is basically when I run these instructions, when I issue a load to an address that I'm not supposed to even access, it's going to bring the data to the cache even before the instruction is going to get committed. So what happens is that even if the operating system says that, oh, you're not allowed to do this and raise an exception and all that, excuse me, the damage is already done, because that value is in the cache. And we already know how to extract secret from the cache. We use the cache side channel attack, okay? And there are other means to do this, right? Yes.
But doesn't the cache side channel just tell us if something's in the cache or not?
What's that?
The cache side channel is just like telling us if something is in the cache or not,
Mhm.
right?
Mhm.
But we already know it's in the cache because we just did this. So like, what is this? What is this really giving us?
Good question. We're gonna actually get into the like examples, but essentially the way it works is that if the address is somehow reveals the secret, then you will know, right? So you don't know. So for example, let's say that there is a secret, and this secret index an array. Okay, so what I will know is that if I know which component of this array is loaded, then I know the index, right? So you have an oracle, which in this case that you know which component exists in the cache and which component does not exist in the cache. You scan through the array and say, okay, item number 2 and 4 and 5 is in the cache, and everything else is not. So it means that the secret was 2 and 4 and 5. So that's how they kind of indirectly read it. That's the main. But we're gonna actually give you example code. Okay, so that's the gist of idea of all of these transient. There are tons of details that we're going to go into. There are different variants, as I said. There are different things that you can do with this, but the general idea is that unfortunately you have this speculative windows that you kind of like let things go by a little bit, and the adversary basically use the exact same window to run things that are not supposed to, and use that in order to leak some secrets. That's kind of like the crux of transient attack. And so accessing something illegal during that window, normally the OS wouldn't allow it, but since this is a speculation, they don't check it at first. They will later be checked. Most of the time, since it's going to be even discarded, the OS will not even know that something like this happened. But then at that point, we have already brought the data into something that the adversary can measure, some channel, which is mainly cache side channel. You have another question? Go ahead.
So I thought that isn't the OS like there's an error in the OS though, right? Because like you try to access the thing and then it tells the OS that this process tried to access some illegal memory.
Oh yes.
But
At some point later.
doesn't
So you can catch that error as well. So it's just a throw and cache. There are ways to bypass the errors, and that's kind of like the main way that this thing will work.
So yeah, normally doesn't the OS just like kill the process?
It can kill the process, but if you catch it yourself, then it doesn't kill the process. So it's
Okay.
right. So I don't know if you've written like these kind of like error handling codes that you catch your own error. So you put that thing inside that catch. So it throws an error, but you catch it and you don't do anything and you continue. But I'm going to give you actually some sample code and you will see that. All right. So before jumping into that, though, we want to do a detour about memory safety and trusted execution environments, because that's kind of important. It's kind of fundamental for understanding the importance of transient. So it's a little bit of detour. So the next few things I'm going to say has nothing to do with what I just said in the previous slide. So the traditional problem in memory and hardware security has been memory safety. Memory safety is a slightly different problem than transient attacks. And basically the idea is the adversary wants to just directly change things from on the memory. So essentially some form of an action to write things. So cache such as mainly just allows you to read things off of the memory. So it's kind of a leakage of secrets. But memory safety allows you to write things to the memory, which cause some form of control over the execution of the system. That's why it's significantly more powerful attacks compared to side channel attack. And this is an old problem. So this is kind of like memory safety problem is like one of the very first problems, maybe along with cryptography, as the main problems in computer security. And to this day, it's still a problem. So it's still lots and lots of people are working on various aspects of memory safety. What can we do to, if we can modify the memory? I think most of you know what we can do, but like, let's say I have a powerful attack that I can just modify memory. What would you do with it? Anyone? Yeah.
Run viruses.
Yeah, you run viruses, right? You inject your own code, you run it. What else you can do? Yeah.
You could run your own code and then also read the other protected memory.
You can also try to then read other protected memory. You can also try to change the behavior of the other part of the memory. You can do a lot of things, right? So then now that that's like a powerful tool. The fundamental question is, okay, how do we modify memory? And then remember that there is an isolation in place, right? So it's not like a process can say that, okay, write to this address, and the system just magically writes to that address. The operating system, as I told you before, usually using virtual addressing or just physical memory protections in order to make sure that you only write to the processes and address space that you're allowed to. You're not allowed to write to other places in the system. So we need to kind of, break this isolation. So how do we do that? We're not going to go through a memory safety. In my other class, where I went through this in more detail, and there are other classes I'm sure you guys are familiar with. But I'm just going to very quickly go over like the basics so that we kind of like have the same level of understanding of these things. So generally, memory safety usually happens because of two reasons. Either you have what we call a temporal dereferencing or invalid inferencing, or spatial. Temporal means that you have some pointer to some part of the memory that is no longer valid pointer, but you are kind of like, use it after it's no longer valid, right? So for example, you you have a pointer like foo, and you free this foo, but then later on in the execution, you try to again dereference it. So it's kind of like called use after free, right? And unfortunately, there are some languages such as C that doesn't really check whether or not you have free this, and then you can access this and you can write this. And there are tons and tons of attacks that people have shown that this can be used for various different reasons of writing things to the memory. The other one is out of bound pointers. This is a more intuitive one, which probably most of you are familiar with. Buffer overflows, for example, that you have a function that's supposed to write to a particular part of the memory, but since you don't check the bounds, you can write to more larger part of the system. How many of you are familiar with buffer overflow? Okay, most of you guys. For those of you who are not familiar, very quickly, we probably want to check this out in your own free time. But generally, if you think about the stack is kind of like look like this. So you have some form of your local parameters here. So these are like, temporary variables that you have for a function, assuming that the stack grows this way. Then you usually have some form of a pointer, like a stack pointer and frame pointer and stuff like that here. But the important things that you have for any stack is a return address. Because any function, when it reaches to the end, it needs to remember where it jumps back. Okay. And where do we store this return address is inside the stack. Okay. So essentially, whenever we reach to the return instruction, the stack pointer points to here. We're going to take this value, and whatever this value says, that would be the value of next PC. Okay. So what the attacker can do is essentially, if this local parameters, let's say, for example, if there is a function or there is some form of functionality that's supposed to write things into this local parameters, instead of writing just like a few lines, I can write many lines if I don't check the boundaries, and essentially I can override the return address, I can override some other local parameters, I can do many things. And as a result, what will happen is that the adversary can basically decide which address this is, because the adversary can write arbitrary values into the stack. Then when it reaches the return address, it basically jumps to wherever the adversary wants. A more advanced version of this attack is that not only it just jumps, but also the attacker injects the code that he wants to execute, right? So not only jumps to that part, that part already also has the attacker's code. There are defense for it such that it doesn't allow you, but the attacker, there are like some other more advanced attacks such as return oriented and so on that allows to essentially create arbitrary sequence. Long story short, again, this requires a separate lecture and separate course. And if you're interested, I actually have a lecture in my previous class that talks about these kind of like, memory safety attacks. And it's very advanced, area of research, lots of attacks and defenses. If I want to kind of summarize it, essentially those things that I said at the top is basically the source of these problems. The source of these two types of temporal or spatial, this is the spatial and this is the temporal, could use to do two things, right? So you either use this pointer, this illegal pointer, to write stuff into the memory, or you use it to read stuff to the memory, or both. Sometimes you need to use it to both. When you have that, then you can do kind of 5 different things. You can modify a data pointer, you can modify some code, you can modify a code pointer, you can modify a data variable, and you can actually output some data variable. The simplest one is that, if I output some data variable and then understand that data variable, that would be an information leakage, right? So if I can't somehow control my code to read arbitrary stuff, I can go and, for example, read the secret key and output it, right? So that's a simple information leakage. That's kind of, this becomes very similar to a side channel attack, because side channel attacks actually do the same thing. But as I said, since you have the capability of writing stuff to your memory, you can also write stuff to do various things. So for example, you can write stuff to modify the code, and then modify the code such that the attacker can run specified part of the code, and this usually goes to what we call code corruption attacks. You can modify a code pointer, so maybe you cannot modify the code, but maybe you can modify the pointer to some existing code, and based on that, you can like run some gadgets or some shell codes. You can have some indirect jumps or returns, but eventually you can execute arbitrary piece of code. This is typically what we refer as to shell code, and this is what we go under the umbrella of what we call control flow hijacking attacks. You hijack the control flow, you feed it to somewhere else in the program memory, and you start executing programs that you wish you want to run. Either these programs are fed by you, right? Or is the existing code that is somehow, if you run it in some way, is malicious. The shellcode one is the most popular one. Shellcode is actually, if I can somehow execute a sequence of a code that invoke a shell, a terminal, then if I have a terminal, then I can run any arbitrary programs in that terminal, right? So the shellcode one is like very powerful and very popular because essentially you're kind of like opening a new virtual computer for yourself. And within that virtual computer, then you can do anything that you want, right? So imagine that you have access to the terminal of a computer. What can you do? Anything that you want. Of course, you might have only have user level privileges and not necessarily root level privileges. There are more fundamental attacks that also even gives you root level privileges. But eventually, let's say even you have user level privileges, lots of interesting stuff you can do as an attack, right? So that's like under this umbrella. You can also modify data values. If you modify data values, this goes under the category of what we call data-only attacks. You can corrupt, numbers, or you can corrupt pointers, and you may not create a new, flow, direction in your control flow, but you just run things in the incorrect sequence, right? So for example, let's say, think about a medical device, right? The medical device has very well-defined sequence of operations. So it has to raise the sensor and then compute, I don't know, like some variable, and based on that, administer the drug or whatever. And then if I somehow can attack the system, maybe I can just manipulate the value that it reads, or move the directions and stuff like that I can do, right? So the attacker does not necessarily need to run other codes. I can just disrupt the existing flow of tasks and instructions within the system, right? So all of these things essentially just starts with that, changing the pointer. And again, why I'm saying these things, because this basically does is breaking the isolation assumption about the system. Okay, any questions? So of course, then you would also wonder that how do we defend against these things? And there's all the range of solutions. The best thing to do is finding the source of the bug and fixing the bug using languages that are generally safe, such as like Rust and so on. There's a whole bunch of software solutions to kind of like test the code and try to find the vulnerable codes. There's a whole bunch of hardware solutions for it. If I want to give you like a few examples, just very quickly, I'm going to go through to like 2 examples. For example, one thing you could do is that you can have some metadata at runtime to kind of check the bounds. So for example, you can say, I always check the bounds information whenever I want to write, or like, I always have some timestamps to know when when the memory address has been freed or not. So, and then I pass this metadata with addresses. So essentially think about each address has some form of this metadata with it. So any instruction that wants to load or store, it basically first check these kind of metadata information. Of course, that means that things going to get slower and your pipeline going to get more complicated. But since memory already is slow, like 100 cycles, 1,000 cycles it requires to access the memory, you can add a few more cycles, right? Like 3 cycles and 1,000 cycles is less than 1% overhead, so it's not a bad idea. There's another thing that is also very popular, and that is control flow integrity, which means that if I'm only worried about control flow hijacking, I can basically enforce the sequence of basic blocks in my system. If I see any sort of like transitions that I haven't seen before, I'm going to flag it as a potential attack, right? So because generally the idea is that if you have a sequence of instructions, as long as the program follows that sequence of instructions, then I'm good to go. As the moment that it tries to jump out somewhere else and start doing some other stuff, that's when my system is in danger. Of course, as I said, data-only attacks does not create that. So this CFI does not apply to data-only attacks, although with some changes you can do that. But the major problem in our systems, such as invoking a shell and all, can be protected by something like CFI. Of course, the CFI itself is also, there are tons of research in this domain. Questions such as, how do I know what are my valid transitions? Because at first I need to know what is valid so that then I can flag the invalid one. How do I enforce this in the runtime? Because then again, so basically what this says is that now every PC, every branch in my pipeline, I need to somehow check whether this target address of this branch is within some known functions, right? So in my front end I need to check, change my BTB and then have another sequence of not only the target address, but also valid target address and all. So there's more things I need to check during my branch resolving, which means that my branch is going to be more complicated. But again, there are works that shows that this is beneficial in terms of getting the security services that you want. And this is just an example of what I mean by control flow. Essentially, for those of you who are familiar with control flow, is that generally we divide the program into basic blocks. Basic block is a sequence of instruction that ends with some form of a jump. And then what you do is that you kind of create this, what we call a control flow graph, or CFG, which you basically just go through the static code of your program and then try to kind of create these blocks. And then what you do is that you need to run this program, right? And then see what are the transitions. So you, for example, see that, from sort 2, you go to sort 1, from label 55, where it is, you go to here, and so on and so forth. So for most of the programs, this control flow graph and this sequence of operations becomes very, very complicated, very, very quickly, unfortunately. That's why there are lots of works of how do you compact this, how do you test this, and so on and so forth, in case you're interested. There exists industry solutions. So there is this thing called Intel Control Flow Enhancement Technology, or Intel CET. This actually exists in most of the modern processors. And what it does is basically kind of does this indirect branch tracking. That basically what it does, and I'm going to show you in the next slide, is adding this end branch, and this end branch kind of make sure that this jump is an allowed jump. So all of your call can only jump to this end branch. If it doesn't see the end branch, then it's not gonna. So you cannot jump to arbitrary part of the program. You only can jump to the beginning of a function. Another thing that majority of modern processors have is this concept of shadow stacking. Since I told you that essentially the problem with this control flow hijacking attack is that you have your local parameters here, and then you have somewhere else in your stack you have your return address, and then what will happen is that the attacker will basically overwrite this. And not only overwrite this, it's kind of start overwriting everything and eventually can overwrite this return. The idea is that why do I store this return in the same place that I stored my local parameters? Maybe I can have a separate stack for just the return address, right? This is usually referred to as shadow stacking, which essentially what we do is that we have the return address stores in a separate stack, which is called shadow stack. And whenever we want to execute the return, we kind of check this value against its copy. If these two matches, means that, okay, nothing happens, I can move forward. If these two don't matches, means that someone, messed with my return address in my majors main stack, so I can actually detect that and raise some exception and so on and so forth. So this is also commonly implemented in many of the modern processors these days, including all of the Intel processors. Any questions from this? This is a little bit more details for the shadow stacking operation. So essentially, after each call, what you do is that you copy this return address into the shadow stack. For each return, you pop the return from both stacks. And then basically what you will see is that whether or not these two matches. If they don't matches, then that means that the system has been attacked. The CET one, let me see. Yes, I used to have, for some reason it's not showing up here. But anyway, there is also, as I said, there is this end branch instruction that basically what it does is ensuring that after each call, we need to see an instruction called end branch. Think about it as like a no-op instruction. And if I don't see that, and I see like an add instruction or any arbitrary instructions, then that will be also indication that I'm jumping to somewhere that I'm not supposed to. So this also kind of saves you from sort of like jumping into random places in the memory, and basically blocks this more advanced version of attacks such as jump-oriented or return-oriented programming. Okay. Another thing that's also commonly used, and this is actually something that we're going to come back to when we were talking about main memory, is memory tagging. I already told you that we can have some metadata. That basically what this metadata gives you is telling you about the time, the timestamp, and the kind of like who has access to this memory and so on. There's actually ARM processors and all of the Mac. Including all of the like newer Mac processors have this memory tagging operation. So essentially, what it does is that it's whenever it wants to write to the pointer, it needs to sign it with a tag, and whenever it reads it, it checks the tag first and to see whether that pointer is matching with the tag. The idea here is that again, if the adversary basically writes write to the memory, right? So like write arbitrary stuff, it can overwrite the pointer, but it cannot overwrite the tag, right? Because in order to overwriting the tag, you need to actually call the secure write function, which you cannot do it over like overwriting stack and all. Okay.
Where's the tag stored?
The tag is stored. So this is actually a picture for ARM. So what they found is that the pointer is 6. So if the addressing is, for example, 64 bits, what they found is that in most of the cases, since your physical memory is much smaller, you're not going to use all the bits in your address space. So they actually use 17 bits for the tag, and then the rest is actually basically used for pointer. So essentially, you still have your 64-bit pointer addresses, but the most significant 17 bits are stored for the tag. And then basically what it does is, takes a pointer, hash it, save it here, and the rest of the pointer basically goes here. During the verifying, you take the tag, you take the actual value of the pointer, you hash it. You compare this pointer authentication code with this hash. If it matches, then you can actually access it. If it's not matched, then you cannot access.
Like, how does this work then? Like, if you do like a malloc, right?
Mm-hmm.
And you get back a pointer.
Mm-hmm.
Does that pointer have the hash in it?
Yes. So like actually like this is actually the assembly code for it. So if I want to, for example, call you have this pack IA authorized access that basically allows you to access to the stack pointer. So underneath it, the underlying hardware basically either like allows you to continue, or if it doesn't match, then it creates an exception here. So cause an interrupt
I see.
basically.
So. What is the hashing like algorithm? Like, can you not just hash it yourself? And then get a valid address, or no?
You can hack. You mean like adversary?
Yeah,
Yeah, adversary can hash it, but the adversary basically needs to call this function. You cannot.
you can hash it like in software.
You cannot hash it in software and write it to that. So this part is not accessible by software. You cannot like have a function that writes to that pack. This is only write by hardware. You can only call this function. If you call this function, you can write things.
But it's just write the memory, right?
Yes.
But you can always write to the memory, no? Like,
You can write to the memory, yes.
so can't you write? I don't it's like where is it like secure? Like, because why do you need to call this hashing function? Why can't you just like,
Oh, so you're saying that when I'm writing to the memory, I also compute the hash?
yeah, and then write that hash also in the memory?
You can do that. You can write that hash to the memory as well with the pointer. But then you need to somehow compute the hash using different. So usually, typically, what they do is that this hash computation can be based on some secret value that operating system knows,
I see.
right? So some secret key. In that case, if you're in the user level, then you cannot. If you're at privilege level, maybe you can.
Okay, so there's a secret that you can't, so you can't software hash it because there's a secret.
You can never software. What you mean by software hashing means that the adversary can
Yeah.
pre-compute. Yes, the adversary cannot pre-compute.
Okay,
But nobody can do software hashing. Just generally, hash has been written by hardware. So it's not software observable. It's not like there is an instruction that I can say that, oh, compute the hash for
but
me.
yeah, I mean, just mean like regular C codes,
Mhm,
like going
mhm.
through doing a hash.
Yeah.
But part of the hash, like the computation is some secret that only the OS knows.
Yes,
That's the
And then-
context.
yes,
And then it gives you back a pointer, and literally like the first like 17 bits of your pointer is the hash.
yes, exactly.
Okay,
With this site view vulnerable attack, so replay attack, if we use a pointer from somewhere else, as a valid path.
Yep. That's actually, I think one of the papers that you're gonna present is there is an attack for this that you can actually. Yeah, you can so you cannot replay it because usually for hashes use the nonce as well. So when you're actually hashing it, the context also includes some form of a nonce. And each time that you hash it, it's generate a different hash. But what people have found is that if I can run this arbitrarily many times, I can basically eventually find the hash since this is only 17 bits, so you can actually brute force it. Yeah.
so yeah, is that question also like, how do you fix that with the, like, you can just do it infinitely many times and
Yeah.
then check? But then also like, so there's a nonce, right?
Uh-huh.
How does, so when you're verifying, you have to know the nonce also, right?
You have to know the nonce also. Yeah, that's why you get the context, right? So.
Yeah, but where is that context stored then?
Well, again, so wherever you store the secret, you can maintain some counter, right? So you can have a counter that
But
stores.
the nonce is gonna be changed by the time you come back to verify though, right?
No, so typically these are grouped together. So there's like, for example, you don't need to continuously change the nonce. So usually you take the address. You use the same nonce, but you take the address, okay? And then together this would be the initial. So for different addresses, you keep the nonce the same, you change the address, that will result in a different hash.
Okay, but
And then you have another like a group. So after a while, you have another nonce group. So you can just, all you need to remember is this nonce group and you can test it with over this nonce groups.
but you still need to like keep track of like, oh, we have this nonce for this nonce group.
Yes. There's some storage, smaller storage that you need to do that,
And
but
where-
that's
yeah,
very.
where's that stored? Is that on the hardware?
On the operating, so whatever operating
Is
system
that in
stores.
the OS level or
Yes.
in the, I see.
Well, whatever is OS stores the secret, it stores the nonce as well. It's because you need to
Okay.
store some secrets. So there will be some kernel space with some secure memory. So you store all of these
And
things.
yeah, like to his point, so then what happens like if you like do the same address twice? So like you have some address, right?
Mhm.
And it's a like, and you just do some address, right? Like legitimately, so you get the hash and then you get freeze. And then later on, you can now go back to that same address if within the same nonce group and you already know the hash.
Well, this doesn't prevent you from accessing the memory. You can access memory as much as you want. This only prevents you from overwriting things to the address. So you cannot change the value of that pointer without updating the tag. Okay, I can read it. As an adversary or as a regular user, I can read as many times as I want. This basically doesn't allow you to corrupt the values. Okay, so
I
that's
see,
a
so then,
protection.
but once you have a combo, right? Like, let's say you have a legitimate combination,
Mhm.
and then like, let's say that pointer gets freed in the code, right?
Mhm.
Then somewhere else, you can now overwrite that somewhere else to have that same pointer that you had before, and you already know the hash because you.
Well, when you free it, you have to also destroy the tag, right? So you have to overwrite the tag. So then the next time that it tries to access it, then it reads that the tag is then no longer matched. Right. So for example, I have some sequence of code, right? And at some point I write the tag, okay? And then if we move forward, at some point I free this, right? Whenever I free this, then I need to make sure that I overwrite this tag. So from this point on, if anyone wants to access it, the tag is from this, it's not from this. So if you try to access this tag, it's already old.
Why is it? How do you overwrite? Is it just a hash?
The same way that you write the tag in the first place, right? So every free is also overwriting the tag. So it's authorized, right? So free is part of the authorized
Yeah, I was
operation.
thinking if you copy the pointer value in between that, right? Before you free it,
Yeah,
then now you have the pointer hash combo,
to
right?
this tag, right?
Yeah,
Yeah, but at this point, if I access it, the tag should match with this guy, not this guy. Right?
The tag is invalidated, like.
The tag has been updated, right? So any action to that pointer will update the tag. If you remember the tag from like long time ago, then only valids during that window.
Okay.
Seems you are very excited about.
I was just trying to understand.
There will be actually a paper. Who's gonna is anyone gonna present this packet up paper? I think it's in the list of papers I can presented, but if generally look at it, it's a very interesting paper of how to attack. Well, this ARM pack is a commercial, it's used in ARM. It actually does work in scenarios where memory memory temporal or spatial is an important thing, but there are some side channels attached to it. But yeah, does this always work? I think you actually, oops, so I'm no longer sharing. Wait, my Zoom decided to update itself. That's great. While I'm using it, it's updating. That's very, that's, yeah. Okay.
Recording in progress.
Okay. Good for you. Oh, sorry about that.
Are you taking a break right now? You taking a break or are you?
No, we're continuing. But now my OneNote is updating.
Okay, I figured out, I Googled my question, I think I didn't phrase my question right. I was wondering like, why can't you just use the pointer somewhere else?
You can use pointer somewhere else as long, so
The
again,
same signature, but I think it's because part of the context is the PC, right?
per process, you can also use it for sure.
But the part of the hash context is the PC, you're trying to put it.
You
at.
use the address, yeah.
Yeah, so I didn't realize that, so then if you put a different address, it's not gonna work.
It's not gonna work, yes. Yeah, usually you either use the memory address or the PC and then, yeah. But again, this is, you're not trying to fix the confidentiality. So it's not like, oh, I'm not gonna allow someone not read my memory. It's just, it's an integrity problem that you're trying to. Okay. So another piece of background that I want to give you, yeah,
Could I
sure.
ask one more question? So
Sure.
this is just basic question for the signing, is that the address of the pointer that we're signing or like the value of the pointer?
The value of the pointer that you're signing, yeah. But usually the context use the address and some form of a nonce to create a unique hash. Any other questions? Good. Yeah, all of the Apple processors actually use this pack. You can actually, I think you can write assembly code with pack. on your Macs if you want to. You can actually play with it because this is actually it's accessible at the ISL level. So there are like instructions that you can use like PACKIA and APIA, authentication and packing. So you can actually write and develop code with this if you're interested.
So this would only affect its newer programs. I mean, if the program is older before the implementation, then that does not contain those instructions.
I mean, like legacy programs, for example, you're suggesting? Like if there's an old program that doesn't have this,
Yes, or that
yeah, you have to recompile to use it, yeah.
be backwards compatible with.
It is backward compatible, but it doesn't have that functionality, right? So if you want, you have to rewrite the functionality as far as I know. But for example, if you have a code that doesn't understand any of these, then you're good because essentially if you don't have this, you're not gonna have this either. So you're good to go, right? So you can write it that way. All right. So second thing I want to talk about before jumping into transient execution attacks is trusted execution environments. Why do we need trusted execution environment? Trusted execution environment was kind of a reaction to a lot of these side channel attacks at that time. It was kind of like a nice and innocent idea at the beginning, but then they realized that, oh, okay, lots of these side channel attacks are directly applicable to unfortunately to T's because many of the principles were the same. And then many of the optimization that used for regular system was also used for this trusted execution environments. So what is a trusted execution environment? The trusted execution environment idea is that let's separate the words. Okay, so let's have some form of like a dirty, like a normal environment where people can access all the things and so on and so forth. You still can have isolation across the processes and all, but all the problems that we discussed in the class is this normal world environment. Then I can have a smaller environment, which usually refers to a secure world environment, which I'm going to have maybe my own operating system or my own hypervisor. I'm going to have my own trusted application. But the majority of the things that I'm going to have here is that I'm going to have two things. One is that I'm going to have probably a different operating system than the normal world operating system. And this operating system is going to be hopefully much smaller. As a result, there is less bugs and less opportunities for the adversary to use this kind of memory safety attacks. The second thing is that I'm going to have some strong hardware isolation mechanisms such that many of these kind of CAG side channel attacks and so on can be basically protected by that. So I'm going to have a very strict kind of access policy on them. Okay, that's kind of like the basic idea of trusted execution environments. So essentially taking the isolation to the next level. Does it work? Unfortunately not. And as we're going to actually talk about transient execution attacks, the main pillar of these T's was this Spectre meltdown. And for example, Intel SGX was like the main thing that was started back then when CAG side channels came out. But then once the Spectre and then tons and tons of attacks on SGX happens, and essentially Intel stopped developing anything with SGX. So nowadays you don't see anything with SGX in it anymore because it's essentially completely obsolete and meaningless because you basically read everything. But so then you also wonder why more isolation? Like what was the problem with the initial observation? Isolation, because essentially people figure out that Windows and Linux kernel gets huge. As a result, there were tons and tons of opportunities for adversaries to find the bugs. So let's go back and have a very small kernel. Of course, this means that you're going to lose some capabilities. So usually that's why you refer it to as rich execution environments and secure execution environments. Rich environment is like your regular system or your normal world system that you can do lots of things. You can, access IO and you show videos and read sensors and all that, because all of that requires complex drivers and complex code. But secure environment is a small environment that maybe can just do some basic operations and so on and so forth. Of course, I need isolation for side channels. I need isolations if I don't trust other vendors and so on and so forth. So that was number one. As I said, this first goal of T's really didn't pan out, although there's still lots of effort in this. For example, Trustzone is trying to do this a little bit differently and is much more successful than Intel. Right now it has this thing called Trustzone that actually can do do nice isolation. Another thing that is happening, coming out soon, is confidential computing platform, or ARM CCB. That is kind of the next generation of this trust zone. But the second use case of T is that this one is actually the ones that kind of drive the need for T's is remote computing. The idea of remote computing is that if I don't trust the host device and I don't trust the operating system, can I still run code in this device, some form of security and with some guarantees? And this actually creates this notion of what we call containers on enclaves. The idea is that within the remote computer, we can create some runtime environment that is completely isolated from the rest of the system. I can run my code there. And there are tons of applications for this, mainly for protecting privacy or confidentiality. And that's why T's are very powerful and very popular these days, because it gives you these capabilities. How it does that, it goes through like some fairly complicated cryptography process that I don't want to get into, but just keep in mind that it actually allows you to have some form of an isolated environment inside your system. Why do I need remote computing? Because I don't trust the hardware or software of that system, but I still want to use that system. Or generally because of regulation. So for example, like things like GDPR, for example, there's a security camera that collects some information. How do I know that that security camera is indeed regulating, following the regulations? I can actually basically install my code there securely and have this sort of hardware guarantees to make sure that it runs correctly. T is basically based on this, that generally you see these different trust boundaries. So depending on what you want to have, typically if you kind of like go with range, as you go higher, it means that there is less trust. So you can have like what we call a trusted application. This is the applications that the trusted entity writes for running on inside the T. Different companies have different terminology for this. For ARM processor, this is called trusted apps. For Intel SGX, this is called an enclave. Okay. And for AMD, generally, we don't have the notion of trusted apps. You have the just general trusted VM. So for the model in AMD is much simpler. It just gives you the entire VM and says, okay, do whatever you want to do with it. This is your thing. You want to also the mess you want to run. That's your thing. Then you have the operating system level. Again, in Intel and ARM terminology, this is usually trusted OS. For Intel, usually we don't have the OS. It's actually the Intel SGX that is at the machine level, basically handling everything. And the rest is actually handled by hardware. But in ARM Trusted, we typically have a trusted OS as a separate thing. Then in ring number 1, we have the hypervisor. Hypervisor allows you to have multiple of these operating systems. Okay. ARM Trusted doesn't have that. So ARM Trusted only has 2 words. You cannot have more than 2 words. But Intel and AMD allows you to have many number of words if you want. So you can have multiple of these that are mutually untrusted. So this one does not trust this one does not trust this one, this does not trust this one, and so on and so forth. Same for Intel, but ARM Trusted doesn't have that. ARM CCA, this newer version of ARM, is actually going to add that. So there's going to be a hypervisor that allows you to have then multiple of these together. Okay? Questions here?
Is an enclave the same as a trusted one?
Enclave is technically the same as, it's slightly different. It's different terminologies for Intel and ARM. So Intel call it Enclave. Yeah. ARM, yeah, Intel has TDX as well, which is mostly supports some memory. I'm not also too familiar with TDX, but yeah, this is a newer version of SGX trying to address some of the problems of SGX. But yeah, I can look up some and share some links in the campus bar. Good. Okay. And then this is kind of like, to give you also a big picture of like how things can handle things. So for example, if I have a bunch of different enclaves, I can also partition my DRAM or my memory to handle this enclaves, right? And then where my like trusted operating system and operating system sits, it also can be partitioned properly. Okay. I can also have, as I said, multiple enclaves and multiple runtimes. In this case, then I have like bigger memory and partitions for the memory as well if I want to. And then I can have even like bigger, like different variants of enclave. So, for example, one of them has runtime and the other one doesn't have runtime. I can then also, what I can do is that I can partition, for example, my L2 cache, right? And then say that, okay, part of the L2 cache belongs to this enclave, part of it belongs to the other enclave, and so on and so forth. I can also partition my peripherals. For example, say that, I don't know, display is only talk to enclave C, and then Wi-Fi is talking to enclave B, and so on and so forth. So that you can actually extend this trust to the IOs as well if you want to. Not all of these systems that I mentioned in the previous slides does that. So this is more of a researchy ideas. And still the like handling free-for-alls is an open research question. So actually one of the things that our lab is working on at the moment. In the context of Boom Core and RISC-V, there's actually an open source trusted execution environment called Keystone. The picture I'm showing you here is for the Rocket Core. Rocket Core is actually the SoC version of a RISC-V Boom. So each of these tiles is basically one Boom core. By the way, this Rocket Core is the in-order version of RISC-V core. So Rocket Core is similar to Boom, but it's smaller. So the names are kind of like, And then, as you can see, the Rocket tile basically has a Rocket Core. It has the page table functionality, page table walking. It has L1I and L1D cache. And then it has this thing called tile bus, which actually allows you to talk to the other components in the system. Then you have some form of a system bus that then talks, for example, to L2 cache, which is basically banks, because L2 is big. You don't want to put it in one chip. You usually put it in multiple chips. And then from there, you go to the memory, right? So AXI is this protocol that we can talk to different components outside your chip, including the memory. Then you can have also your peripherals. For example, you can have, the peripheral bus and peripheral bus, any sort of like, connection that you want to have to your system. But essentially, your trusted execution environments can be implemented either as some form of an accelerator within this T here, or it could be as some form of a peripheral that talks to the system now. So there are different ways of you can assume that this can be implemented in some cases. This is just the terminology of RISC-V, so there's nothing special about this, just terminology that you see. This ROCC is an accelerator, like rocket accelerator that basically your keystone can be implemented there. In the terminology of the keystone, these are the names that you will see. They call it instead of trusted app or enclave, they call it enclave apps. But it has 3 layers. So it has user level, supervisor level, machine level, and trusted level. So those 4 rings, ring 0, ring 1, ring 2, ring 3. So you can ring 3, ring 2, ring 1, ring 0. It can have a trusted runtime. It can also have a security monitor, so you can have actually multiple of these if you want to. If you don't want to trust these from each other, you can actually, the security monitor allows you. And of course, at the hardware level, there are hardware features that allows you to access the system. I showed you this picture before, and now you kind of understand it a little bit better. This is from Keystone. Essentially, Keystone gives you various different capabilities. For example, it allows you to partition your cache if you want to. It also allows you to do encryption between the main memory and the cache. This encryption can be hardware-based, can be software-based, and then it could be also coupled with this partitioning of the cache if you want to. So in a regular system, you don't have anything. If you want to partition the cache, you can actually partition it, and then you can, at the most, secure way of like grade, you're gonna have both encryption and partitioning if you want to. So that's what Keystone gives you. Keystone also part of the Boom Core and Boom Core ecosystem. If you're interested, you can definitely take a look at their documentations. All right, so all of these things we are saying, now the question is this enough and does this work? And that's basically gives us back to what we were talking about, and that was the issue of transient execution attacks, that essentially by creating this illegal window, unfortunately, the attacker can attack the system. Let's have a quick break and we're going to go through the details of transient execution. Let's continue. Okay, so as I said, the general idea of a transient execution attack is that in the victim domain, what the attacker does is it waits obviously first for the victim to access some secret. Then it use some trick that we're going to discuss to transmit this secret across some channel to some domain that the attacker can receive it. So the one that we are talking about mostly, and is for like the most popular one, is the cache. This part we already know how it's done. That if I know that there is a particular address or sequence of addresses that I want to read, how should I read them? I can use prime and probe and flush and reload and stuff like that. Just keep in mind that cache is only one example. There's actually tons of papers that shows that there are other examples of attacking and that designing that reception function. But let's actually talk about how do we do this part. How do we trick the user to access some secret, and how do we transmit this secret to the attacker's domain using some side channel attacks. So what we want to see is what we can read and why we can read them. To understand that, the first thing that we're going to talk about is the meltdown attack, and this is kind of like the very first attacks in this domain. To understand how meltdown can work is you have to like quickly understand that we usually want to map the kernel space within the user space. So if you think about the virtual address space of a process, usually the most significant bit, the half of the memory is used by the actual code that is used by the user. The second half of the virtual address space is basically the kernel space that is mapping to the user space. So this is not a real memory, it's only mapped into this so that it can actually be quickly used. Why do I want to do that? Anyone? Why do we map the kernel space into the user space, for those of you taking operating system courses? You want to say?
No, I have no idea.
Yeah, go ahead.
I spent like 2 hours last week looking at this. But I think it's because so when you have like a interrupt, you do a system call on
Uh-huh.
kernel.
Uh-huh.
It doesn't have to switch processes, it just switches to kernel mode.
Yes.
And then it can, without flushing the cache and everything, it's still the same process. It can run kernel functions during your system call without switching. So
Yeah.
then it can switch back.
Yeah, exactly. So think about kernel as this service, utility service, right? Is these functions that you want to call, the printf and the scanf and those things that you write in your programs, right? In order to use that services, this is typically translated into some form of a system call, okay? So this system call needs to be serviced by the kernel. That's what's the job of the kernel is that, okay? You have two options. Either you treat kernel as a separate process. As a result, each time that you, for example, have a printf function, that means that you have to have a context switch. A context switch means that one process has to stop, the other process has to start. Context switch is a process that you need to clean up the cache and you need to flush the L1 and L2 in some cases and so on. You need to redo your branch predictors and all that. So every single call for like something like this would require a lot of overhead. And that's also not only kind of like this process takes a lot of time, but also this means that all of your nice things that you had for spatial and locality and temporal locality for your caches going to be basically flushed out, because the moment you run this all the previous history is gone. So your branch predictor gonna perform terrible next time and so on and so forth. Okay, so what do we do instead? We map this into this such that then it doesn't require you to flush out everything. It's just basically you just switch the modes because you trust the kernel, right? So the kernel can access things in the user level, that's fine. User cannot access things to the kernel level. So that's the main criteria for this thing to work, okay? How do we do it securely? Jacob, that you have learned, how do you do this securely? How do you implement this?
I guess you just do.
You think,
Well, it's protected, right, like the memory,
yeah, so what is the,
like the page table,
yes.
so the page table
Yes,
has like.
exactly.
Bits that tell you.
So if you remember when we were wanting to translate address from virtual to physical, we had to go through the page table. So all we need to do is that we have an extra, remember I told you that usually within each page table entry, we have some kind of like flags and extra metadata. One of them is that, is this a kernel page or not, right? So then for all of these kind of orange-ish, that bit is equal to 1. And for all the green ones, that bit is not equal to 1. So that if this guy wants to access this, essentially all he needs to do is finding this address. This goes through the page table, see that it's a kernel, it gives the access to the kernel. If the other guy wants to try to read this, they don't have the privilege to do that, so it will be blocked. Same way that isolation can help you. So if, for example, this tries to read some other address space, it's going to be blocked. Same way, it's going to also be blocked with the kernel. So this is technically, on paper, at least, is secure, right? So because as long as isolation is secure, this is also secure. There's no problem with it. Okay, any questions here? Great. So how do we abuse this? We abuse this using this bug in the system. And remember, these are transient execution tag. So just imagine that I have a code like this, that is like some kernel address and some secret value. Then what I'm going to do is that I have some form of an arbitrary probe array that takes this secret and basically index through that probe array. Okay. So now imagine that what happens is the following. Okay. Let's say, for example, this one is like L1. This is like accessing L1 D cache. And this one is an access to L2 cache, okay? You can actually set things such that it works this way, but for now, let's just imagine that this load, because this is a load, right? So it loads the value from the kernel address into this variable secret, but this is actually a load that might end up in L1 cache, okay? And then the second address, which is again the value here, and this one reads from this probe array, and probe array translates to an address, which happens to be stored in L2 cache, okay? So two possibilities exist here, right? So the possibility number one is that L1D starts, right? And it finished the execution before the data from L2 comes, okay? The other option is that, so at this point, since this value has been arrived and finished the execution, and then we commit, we will realize that, oh, this address belongs to the kernel. That will cause an exception, right? Because user level are not supposed to read addresses from the kernel. So this in real world should cause an exception because the user does not have the privilege, okay? But what could happen in some other cases is that if right before this commit happens, basically, right? If this access request to L2, okay, so if we send this access and go and read the value L2 happens before this instruction commits, and we realize that, oh, we were not supposed to access that. If this access is gone, then it's gone. There's no way that you bring this back, okay? So essentially what you do once this access happens is that you're gonna go and bring the value that is basically based on this secret times 64, and the 64 is just to make sure that, it's like basically based on the page offset and so on. It doesn't matter at the moment. But essentially what will happen is that this dummy value, we're gonna get some value for this at some point. So you're gonna be brought into L1. You're not going to see it at the C level, at the user level, because it's going to be blocked by the operating system, but this value is going to exist in your L2 cache, okay? So what do you do next? That you can basically run a prime and probe attack on this. What do? You essentially take this and say that, okay, I'm going to basically know where these addresses going to be mapped into my set. So let's say, for example, from secret equal to 0 to whatever number that we are probing, each one is mapped to a different set, okay? So let's say, for example, 64 different sets, all right? So what I'm going to do is that as an attacker, I'm going to do a prime and probe. So I'm going to basically fill this set with my adversarial data. Each set, I'm going to do all of them, okay? So I'm going to do all of these guys, and I'm going to fill them with my adversarial data set. Based on the secret value, one of these guys is going to be evicted, right? So for example, I don't know if secret is equal to 2, if this is 0, this is 1, this is 2, this guy or one of these guys is going to be evicted, and it's going to be with some dummy value. I don't care about the value. I just care about that this is going to. Then I'm going to do the probing phase. I'm going to go through this sequence of addresses again and see that, line number 2 is the one that's been actually kicked out. That means that my secret was 2. And at this point, I did not access the address. Remember that the exception works well. So indeed, it was, at some point, this was committed and the exception actually happened. But still, since this has been brought in the cache, it has this effect, and I can observe this effect as an adversary. Yes?
You remind me what the point of multiplying by 64 is. That's just the cache line size of 64.
Yeah, I think this is in this particular case. I mean, I just grabbed this from the original meltdown code. But I think, yeah, it's just make sure that, you have the right offset for, I think, to go to the next cache line. Yeah. Yeah.
So is the exception just making sure that whatever's in their kernel address isn't loaded into the secret variable? Is that what it's basically doing, that everything that moves around in the cache will say?
Yeah.
That happens before the exception zone.
So if you remember that we said that essentially the way that systems work correctly is if someone tries to access this line, it will cause an exception. The operating system does this exception because this is a user level access that is trying to access a kernel address. This has to be blocked, and it's blocked by an exception. What the adversary does is that it doesn't change that behavior. It just manipulates the timing. It basically says that if I'm lucky enough and the time it takes for the operating system to realize that this was an exception is bigger than the time that this guy is actually accessing the L2 cache, so this time is smaller than this exception time, then the damage is done because then things has been loaded. In my free time, I'll just like maybe an hour later or a day later or whenever I want, I can go and scan the L2 cache and read that data. Although you have to do it very quickly because other things might mess up with your L2 data. But I mean, hypothetically, if no one else touches L2, you can just read it whenever you want. And then someone asked like, oh, okay, well then if the exception happens, wouldn't that crash the whole program? Again, if the program crashes, the adversary can still launch another program. But typically, what do? You put this into a throw error, kind of like a block that you catch your own error, basically. So what you do is, because this is the adversary control code. This is not like a code written by victim. This is a code written by the adversary. The adversary basically put this into some form of what's error, like exception handling code. So you basically just ignore the exception, just move on. Okay. Yeah, this is just basically the algorithm said the attacker allocates a probe array. Let's say, for example, 256 cache lines. It flush all the cache lines. It waits for the attacker to execute the code above. The attacker will basically access one of those cache lines. The attacker can probe and find that exact byte, and that reveals the secret. Okay. There is another, as I said, this is one example, and this is meltdown example. There was also a Spectre example, which is actually a slightly more sophisticated. So the spectrum attack is basically instead of using kernel address space and using the exception handling, it uses the notion of branch misprediction. So what does it do? It basically does this thing that it says that, let's say I have a branch. For example, branch is x smaller than some array size, some value. Okay. And then I have these two sequence of code, very similar to the one that we had before for meltdown. Here I'm accessing some array x, right? And then here I'm using that to index some probe array that I want. Okay. And then again, if assuming that this first instruction is going to be mapped into L1 and the second instruction is mapped to L2, if I get lucky and the time that for this to be issued is before that my branch is resolved, which in this case, for example, if this size array is not in L1 cache, it's actually a value that needs to be loaded from the memory, then this will take a lot of time to be resolved. But then these two guys can basically go ahead, okay? And then, for example, what you can do is that at some point you can actually realize that, oh, this was a misprediction and nothing happens, right? So it was a misprediction and you move on. But again, as you can see, this value has been loaded to L2. The attacker can do the exact same thing as I showed you before. That basically goes through the L2, do the prime and probing of flush and reloading or any other type of attacks and read this value, okay? The main thing about this second one, that this is actually not even a bug. This could be like a completely legitimate code and you still see this observation. Yeah.
So this is like code that the attacker is writing, right?
It's a code that the attacker writing. It could be also code like this could exist in many systems, unfortunately.
I guess the idea then is like, if this code the attacker has, and they can directly access array one for the secret, like, what's the point of this attack if they can just access the secret?
So no, that's a good question. So what the attacker does at this point is that this X could be any arbitrary value, right? So it doesn't need to be within the range of array one. Array one is what the adversary can access, but this X could be 1 million, right? This access will result in some address in the memory that you're not supposed to read, but remember that again, we don't check, right? So we issue the load without checking. We only check when we know that this is not speculative. So that's the whole like basically with this, I can choose any address I want. So it no longer is even kernel. I can basically say that I want to read this arbitrary address at this place. You put it there and it works. Another thing that you usually do for making sure that this attack works is making sure that your branch is always predicting the taken path, right? So you want your speculation to go through this path, because if you speculate and you jump over, then your attack won't work, okay? So there is actually usually a sequence of training the branch predictor to think that it's always work. How do I do that? I can basically run this code many times with X smaller than array size. And this actually results in a legitimate code being executed in the system. And then train this branch, because remember that the branch using history, right? So if it sees that all the histories of this particular branch is always taken, then the next time during the actual attack, I make this X really large. It still predict taken, but in fact, the X in fact is much bigger than it is. So there's like it's kind of an offline phase that the adversary can do to train this predictor. Otherwise, it's kind of like a flipping a coin. Sometimes this attack works and sometimes it doesn't. But if I train it correctly, then it's easy to train. Another thing that, for example, people have shown is that they don't need to train this branch predictor. They need to find a branch that happens to be alias with this branch. Because remember, we check like this, here's some history of the branch, right? So if I can train based on some other branch that happens to use the same index and history with this, then basically you can attack this. So it's going to be the next level as well. So you can write your own code, you can train your own branch predictor. As long as hardware history is the same, which is the case for all the branch predictors in the modern computers, then if you train it on your own branch, you can also mess up this branch. That's the main thing that is happening. Unless like one defense would be, okay, let's have different branch predictors for different cores and all, which is expensive and no people don't do that. Does that make sense? So you train your branch predictor, you trigger the branch to mispredict, then your array, you map it to whatever arbitrary address that you want. For example, it could be a kernel address, could be another process address, and so on. And then probe the cache to find whatever address that was. Okay? Yes.
These don't seem like too crazy. Like, why did it all of a sudden blow up in like 2018? Like,
Well, it was discovered as like, are you asking like why it took so long time, or?
yeah, it feels like this is kind of like,
Well, there's always like a great research seems trivial, so that's like always like it's a very known. So most of these good research is always like when you know it, it's like, oh yeah, like it should have been like that. But yeah, you can argue also like I don't know, Maxwell equations was trivial. Quantum computing is trivial, but yeah, it's trivial. But I would say because cache side channels wasn't a thing until like 2014, 2015. Also keep in mind that out of order execution wasn't like a big thing until like early, like it was like starting early 2005, 6. So it's only 10 years after that. So it's not like a long time.
I guess for my whole life.
Yeah. So it's not like, like processors been around since like 16th century and like, right? So that's another reason. But yeah, generally, if you see something is very trivial, that's actually usually it's a good sign for things that works. Similar to machine learning, actually, like AlexNet, for example, was like became a thing in like early 2010, but like many of the ideas was around for many years actually. So why this is significant? Well, why it got a lot of attention from the industry and the research community? Because it's extremely challenging to mitigate, especially the Spectre one, because the meltdown one is slightly more easier to. It's basically some form of like, exception needs to be handled more quickly and faster. If I can, handle exception faster and patch the software such that it handles the exception right away, the problem is gone. But branch misprediction is something that you cannot do anything about. It's just fundamentally limited by the operands of the branch predictor. If you had known the operand values, you would have predicted the branch earlier anyway. The problem is just it's fundamentally the problem is fundamental. You cannot do anything. And as I said, this is it's not a bug. It's just the general operation of your process. So as long as you don't change the speculation and then you just completely change your pipeline and assumption, you cannot really fix this. Okay. And then the second thing is that the impact is huge, right? So the adversary can basically virtually read anything that they want, including all the addresses that in the virtual space and so on and so forth. Next time, not the coming Wednesday, Monday, because that's a presentation, but on Wednesday, we're going to actually talk about the defenses. And you will see that there are some good defenses, but still it's challenging to fix this.
What is a gadget?
Where's the gadget? Gadget is this. This sequence of code that kind of like you have an if, and then you have some secret value that is running through this is a gadget. Gadget generally is like a sequence of codes that you run. So Spectre has other variants as well. Another very popular variant is branch target. So you can actually combine these variants together or use this variants for different things. So the idea of the variants too is you can also poison the target address. So not only the direction of the branch, you can also poison the branch predictor to jump to arbitrary points of the program. For example, if I have a sequence of code like this here that is not within the if then else, what can I do? Instead of training this branch predictor to always be taken, I can train it to be not taken. And another thing that I can do to train is that I can change the target address to be this address. So remember that we also not only we had the direction of the branch, we also remember the target of the branch. So if I can poison the branch predictor to also incorrectly remember the target, then I can not only cause a misprediction, but also say that, whenever I want, you jump to this part. Again, this will be flushed out of the pipeline because this is not a true sequence of the code, right? But this is prediction, right? So you can make a mistake in your target address as well. There's no one says that your target address is always correct. It jumps there and it realizes, oh, what the hell is this? I should have go ahead or should have jumped somewhere else. You squash things, but again, if this time that you realize that you have to squash things is smaller than this time, then you're screwed, right? So the value is loaded into L2 and the attacker can basically run it at the same time, at any time that they want. So this variant 2 is actually makes this Spectre attack significantly more powerful, because then essentially you're not limited to like, codes that within an if then else block, you can basically jump to virtually anywhere we want to the program. So it becomes a very deadly sequence. So if you look at the kind of like the root cause of this Spectre type attacks, is that you have some operation n, and then this is basically time. Then you make some prediction, right? So, and then that would result into operation number 2 or some type of operation there. And this kind of sequence of this prediction is basically the transient execution window, right? At some point you retire this operation, and again you kind of continue until you kind of realize this prediction was wrong or right. And then you will basically decide that, oh, okay, this prediction needs to be retired. And that's when you realize that you have made a mistake or not in this case, right? So you kind of like, get rid of this instruction or not. But as you can see that basically what it does is that during this time, you are essentially revealing some architectural information outside. So this is why fundamentally there is not much you can do in terms of protecting the system against this. This is just a natural operation of the system that you want to have a prediction and then some other operations while you're predicting, and that operations can be computed or misused by the adversary. Okay. This is many variants of Spectre. There's like V1, 2, 4, 5, Spectre BTB, RSP, Retrospect, Net Spectre, and then there's Meltdown, a different version of Meltdown. There's Zombie Load, there's Foreshadow and Foreshadow Next Generation, and L1 Terminal Faults, and then there's Riddle and Fallout. I think some of them are actually going to be presenting in 2 weeks for those of you presenting transient execution attacks. I think Fallout, for example, is like fairly new, and you're gonna some of you are gonna present that. But generally, it's a good friend of mine, Daniel Genkin, which is actually like the main author of many of these papers. He was always saying that his students are trying to like create logos. So like his criteria for hiring PhD students is someone who can create good logos. But yeah, as you can see, there's like a lot of logos and a lot of names, and generally like just like explosion of different attacks in this domain. So yeah, there's like lots of interesting stuff happening in this space.
In the previous slide, what did it mean by predict CFDF?
Control flow, data flow. Yeah, so it's like which direction flows. Any other questions? I think we have a few other variants as well. The one is, for example, Foreshadow. Remember, I told you that there is a trusted execution environment, and trusted execution environments are actually kind of blocking accesses. So Foreshadow actually tries to attack that. What they found was that there's this very crazy bug in the cache system and page tables. So this is the sequence of code for Foreshadow. You can actually take a look at it later if you want to. It basically used very similar idea of Meltdown. So it tries to kind of like have, actually, let me show you the C code. Maybe it's easier. So it tries to, again, like as you can see, it tries to access some address that is not supposed to, which could cause some exceptions. But what it does, it basically sees that, let me show you the next slide. What they found is that, remember I told you that there is VIPT, the virtually indexed physically tagged cache in L1. So what happened is that, when you have a virtual address, your virtual address needs to be translated by the page table, right? But to save time, you also access L1D at the same time in parallel, okay? What they found is that essentially with this, if the page that you're trying to access is not in the page table, but the value is actually existed. So this is actually like, there is this another flag entry in that page table is called present. They found that if the present bit is 0, the rest of the values is still there, just the present bit is 0. So if it goes to the page table lookup, it's going to take some time for the page table to translate, but the values are there. So it's actually like if you do the VIPT, the L2 L1D cache is going to be a hit. So it actually generates the tag and everything, and that will result in a value that can be like actually loaded back into the out of order execution. So they based on this, they can actually load any arbitrary value that they want using the same pattern as you can see here. So this oracle is essentially the same dummy values that they do, and then based on like the slots, the pointer, they can basically read whatever value that they want. So this pointer is the pointer that is accessed by the victim, basically. And then you can read arbitrary values. And this interesting thing about this is that, as you can see, this means that I can then read across the domains because even if the page table does not translate the pages, as long as the virtual address is the same, the lower bits is the same, I can access the L1D cache and read things off of. This is also very interesting. Another variant of foreshadow is foreshadow next generation, which again, you can not only do this, but you can have like a virtual machine that can control this page table accesses and like play with the page table and actually inject some dummy page tables and all that. So can actually be very powerful with this. You can read arbitrary pages from any process in your system, which means that essentially all of the good things that Intel SGX and all did, that was completely broken by this. And that's again was one of the key reasons that Intel SGX didn't really continue. What are the other options? There are many different ways to read the data. That's why you have seen those many variants. There are many ways to trick the branch predictor. There are many ways to extract the to secret. And you multiply these, and then you will get the explosion of different attacks. We're going to see some of them in the paper presentations. I think this is the last one. There's another one called zombie load. The zombie load, basically what they found is that if there is a load that is stale, so it's no longer used, if there are future stores, what they found is that the load store forwarding doesn't check whether things are stale or not. It basically forward things because it basically goes through tags. That's all it does. So they found that the attacker can basically get values from the victim by the load store forwarding if they do it in the right time and time it well with the execution. So it's kind of like a load that has been zombied and the attacker can basically use that. There are details for it. I think zombie load is probably another paper that we're going to be presenting. But if you're interested in any of these, I definitely recommend you to go and take a look at them. How do we fix this? So anyone wants to suggest how do we fix these things? Next time we're gonna actually talk about it, but let's see if there are some ideas. Yeah.
I mean, one fix that's like awful, but you can do it is just disable speculation.
Disable speculation, right?
For
Like
loads and-
close the transient window. That's one
Or-
like literally that's one way of doing it. Yeah.
Yeah, I think like a lot of these attacks are on the basis of when you're speculating, you don't actually check like if your access making illegal access. Why don't we just like
Check.
we would check if that's the case.
Yeah.
even speculation.
Yeah, we're gonna talk about that. It's not gonna be easy because in order to check, you need data to be available, and we don't have that data in many cases. But yes, it's possible to do that. It's not. There is like this notion of what we call visibility point, that where other people see. So, for example, I issue a load, But I don't need to make it visible for everyone, so maybe I can do some other things, so we're gonna talk about it next time, yeah.
I mean, since we're also bringing data into the cache, and we don't know if the actual instruction is speculative or not, maybe delay bringing.
Delay the load, yeah, but keep in mind that delaying the load is very bad for your performance, right? You had one thing to say.
Yeah, I was gonna say something similar where it's like, okay, why don't we just don't. We, like, if we're speculating on the instructions, why don't we wait to cache the data until the instruction is committed, and then we can like forward from some intermediate microarchitecture structure. Instead of using the.
Well, then the adversary can read that intermediate, right? If a regular process can access that intermediate, the adversary, like cache is your intermediate, right?
I guess in that case, just like don't cache until you commit.
Yeah, no caching you commit, but yeah, good luck with selling that. Yeah.
I was gonna say maybe, well, now I'm thinking about it, but maybe like. You have something like a special tag on speculative like loads and. Maybe you make them wait.
Mhm.
So to be as if you had missed the cache, but it's already there.
Mhm.
So you just kind of, or maybe like something so it's noisy, so something like that. So like you put a tag on it that says like, this was speculative. You kind of have to like do something different when you just keep, even if it's in the cache. You kind of maybe you add some noise to that, to how long it takes.
Maybe, but keep in mind that the adversary doesn't read that value, it reads an own value, and problem is that once you bring that thing to the cache, you're kicking out the adversary.
That's true.
Right, so you have to somehow say that, oh, this is a speculative, don't kick out anything else or
Okay,
something.
maybe you could have a speculative cache.
Yeah, a speculative like a
Separate-
buffer that you put it
separate
there,
cache, only
yeah.
for speculative stuff.
Mhm.
And then once it's committed, you move it over to the real
Yeah,
cache.
but then what if your DAT fills up, right? So like if there are many of those.
Then it goes to memory and it's awful performance, but then then I guess you've designed your processor wrong.
Yeah.
Because it doesn't not size correctly.
Anything else? Yeah,
So these attacks like Meltdown also have like a setup phase where they're kind of doing something with the cache, like manipulating it.
Mhm.
Like they're filling it with the eviction set. Is there a way to detect that and then you can
Mhm.
stop the process from?
yeah, if you can close the channel, then that works as well, like for example, any sort of defense that we mentioned for cache. Directly applicable here, right? The only problem is the adversary can also find other channels, right? So for example, cache is not the only channel that the adversary can use. So you close the cache, but then they use like branch predictor or other channels to extract it. Any other suggestions? No.
I'm trying to detect if the like branch predictor is being like manipulated.
Manipulated, yeah.
Trying to go to an arbitrary.
Yeah, yeah, maybe it's with branch prediction, misprediction detection, yeah, or even try to isolate your branch predictors, that's also helps. Any software solution? Everybody is like changing. First of all, these are good solutions. We're actually going to talk about them. But now you know that this does not apply to legacy systems. Like we have thousands and thousands of processors already in the market. How are you going to fix those, right? You cannot. Yes, for future systems, you can change this and that and like delay loads. But there are existing software, existing CPUs installed in your aircrafts and tanks and all that are already like vulnerable, right? So you need to find software solutions as well. Yeah.
I was thinking about the meltdown ones, is related to like how the instructions are active. We just simply slow
Slow it down.
Yeah.
Yeah.
Make sure that the second instruction is called.
Yeah, slow down the second load or something. Yeah, that could also work.
So like, the whole idea with memory safety, right? Like if you just convert program to a memory safe language. I mean, it's probably expensive to do that. If you do that, then if you try to like, for example, access a kernel address, then maybe at compile time will block you from even compiling.
Yeah, so you can have an equivalent of like a memory safe language with like side channel safe. So you can identify these leakage patterns and then remove them. So that's actually another very powerful way of doing this. Although detecting them might be a little bit difficult, but that's actually one of the key methods to protect it. Anything else? I think we covered most of it, yeah.
Well, I mean, you can't always do that, right? Because sometimes like your code logic, you just need to like load something from memory and then check it and then do something depending on what you get there. So you can't really.
Yeah, that's true.
You can't.
At least you
like-
know, and then if you know that this is your secret, then you know that you're vulnerable, right? So
You could always, then I guess that's true, then you could maybe add another, you could check, and maybe you could have like extra instructions that's like.
yeah, you add like some
Is it
dummy in
speculative?
between.
Or not even that, you could just tell a CPU like, this block is speculative
Yeah,
and like, and it's like dangerous to link these
Yeah,
two together. So like, for this specific instruction.
turn off the speculation. Yeah,
Don't speculate for these
Yeah.
instructions here.
yeah, yeah.
The form would still be terrible and everything before gets thrown out. So I'm assuming there's ongoing speculative execution at that time, that could be thrown out.
You
Yeah.
can say that these instructions specifically, don't speculate on these ones.
Yeah.
Like these next few instructions in the, you know, like the next 10 instructions, don't speculate, because it's kind of dangerous.
Yeah, so
That,
these are good points. We're gonna get to it.
so,
There are all combination of those that you can do. But we're gonna actually go back to this conversation next time. Quick takeaways before I let you guys go. So speculation just generally fundamentally bypass isolation. We combine it with a powerful side channel attack like, cache side channel, and then boom, you have leak the secrets. Defense against it, unfortunately, is very, very challenging because it essentially just needs to fundamentally change the way that we operate things in the processor. But it's also quite active area of research. A lot of people is interested in looking at solutions, which we're gonna go over. Don't forget the reviews. I'm gonna actually post a Google form link tonight, and then computer assignments, work on it. And then the next one is gonna be also out the moment that we finish the first one, okay? And then next Monday, we're gonna have the paper presentation, so be prepared.
Are there like actual dates for that?
Due dates is the same day as the paper presentation. Yeah, we can talk offline.